Okay, so yeah, we start the afternoon session. The speaker is Kokubo-san. Yeah, please go ahead.
Thank you, Ida-san. So hi, everyone. I'm Eiichiro Kokubo. I'm sorry, a few days ago, I lost my voice. So I use microphone today. So first of all, I'd like to thank the organizers to organize this meeting. So I'm enjoying this very much. So today I'm talking about the orbital architecture of planetary systems formed by gravitational scattering and collisions. Sorry, my talk is mainly for bound planets. But by applying the result, let me discuss a little bit about the planet ejection too. Okay? So let me start my talk with introducing this exoplanets on the semi-major axis mass plane. So in this talk, we focus on this population called as closing super Earths, including our terrestrial planets. Yes. So we focus on this area of planets on this plane. Okay. So first, let me explain a little bit about the closing super Earths. The definition is like this. So the radius is smaller than about 4 times the Earth's radii, and their orbital periods are less than 100 days. So which corresponds to 0.4 AU for solar mass stars. And these systems have these remarkable properties. For example, most stars host this kind of planetary systems independently of their metallicity. And most of them are multi-planet systems with mean multiplicity of about 3. And for their period distribution, so we know this log normal period ratio distribution with slight excess around low order mean motion resonances. And for the orbital separation of adjacent planets, so if we scale the separation with their mutual hue radius, it's about 20. And compare with giant planets, they tend to have smaller eccentricity and inclinations of order 0.01. Okay, so this cartoon compares the solar system terrestrial planets with the closing super systems. They are very different. So we like to understand the physics, the background of this apparently different orbital architecture. So let me introduce now giant impacts. So giant impacts is collisions between relatively large-sized objects. So in the context of planet formation, they are protoplanets or planetary embryos. And giant impact stage is considered for the final planet formation stage of terrestrial planets in the solar system, and also for the final formation stage of closing super Earths in some leading models. So on the giant impact stage, the physics is very simple. There are 2 physics operating: the gravitational scattering between planets and their physical collisions. Since we have giant impacts only after the disposal of gas disk, so the system is gas-free. So the question here is, what kind of orbital architecture is realized by giant impact evolution? Okay. So then we investigate this subject using numerical simulations and body simulations. So we start simulations from embryos. Okay, so like this cartoon shows. So for initial embryo conditions, we assume the mass distribution following this power law distribution, with sigma 1 is the reference surface density at 1 AU, and alpha changes the mass distribution over radius. So we vary alpha and sigma 1 like this. And for protoplanet parameters, so we assume the isolation mass of embryos, and we vary the range of distribution, and also the orbital separation between 2 adjacent planets, and also we vary the eccentricity and inclination of their orbits. And we fix the material density for this time, 3 grams per cubic centimeter. And here for simplicity, so we assume just stellar mass is just solar mass. And this is, of course, gas-free. And planets are just uniform spheres. And we assume perfect accretion, so which means all collisions lead to accretion. And we integrate the system 5 times 10 to the 8 orbits of the innermost planet. And since the evolution by giant impact is very chaotic in nature, so for one protoplanet model, we perform 20 runs with initially different angle positions. And we calculate some statistics, like the median, orbital elements. Okay. And after the simulation, so planetary system is formed, then we calculate the system parameters. So this talk, we focus on 2 architecture parameters. One is mean orbital separation scaled by the mutual Hugh radius. So this is calculated for a planetary system, okay? And also in the same way as the mean orbital separation, we calculate the mean eccentricity of the system scaled by the Hugh radius in this way, right? So here the numbers in magenta, those for the solar system terrestrial planets, 43 and 5. And this is the definition of mutual Hugh radius, you may know, right? And we calculate mainly the median and the median absolute deviation mark from 20 runs for one model, okay? So now let me show you an example of the evolution. So here, initially we have 15 embryos, and after 5 times 10 to the 8 Kepler, a period, so the system only now consists of 5 planets. So this is the semi-major axis evolution against time, and this is the evolution snapshots on the semi-major axis eccentricity plane. So we know the gravitational scatterings on average increases eccentricity and inclination, while collisions on average dumps the eccentricity and inclinations, while increasing the orbital separation by reducing the number of planets. So in this particular example, so the separation expands from 10 to 23 and the eccentricity from 1.4 to 3.5. And they are not in resonances. So this is an example of one run. So now let me show you the statistical evolution over 20 runs. So here I plot for one model with these, the parameters for embryo system. So this is orbital separation and eccentricity and inclination scaled by the Hugh radius over 20 runs, median and mark. So you see, initially in about 1 million years, the system is stable. So no change in orbital separation, meaning the number of planets doesn't change on this stage. So after this time, the system becomes orbitally unstable. Instability takes place, Then giant impacts start. So by increasing the eccentricity and inclination first, and then they saturate to some certain value, and also expanding this orbital separation, but it saturates finally. So now we like to know what determines this final saturated parameters. And since the inclination behaves very like eccentricity, we focus on the separation B and the eccentricity in hereafter. So now we vary the disk parameters to see how the initial condition affects the final orbital architecture. So here we change sigma 1, reference surface density, and also the alpha, which controls the mass distribution over radius. So this total mass, sigma 1, changing sigma 1 corresponds to changing the total mass of the embryos. So we have B separation and E against total mass and alpha. But as you see here, both of them hardly depend on these parameters. So here we see the beautiful Hughes scaling. So Hughes scaling is known for purely gravitational dynamics. So that So if the dynamics is purely dominated by gravity, so locally, the Hill radius scales the orbital architecture. Good. And then now we change the orbital parameters of protoplanets. So here we have initial separation of two adjacent planets and initial eccentricity. And again, B and E. So again, they don't depend on B and sigma E. So that's good, very simple, right? Result. So we have this huge scaling. So now we change the location or the semi-major axis of system. So now, so against the mean, mass-weighted mean semi-major axis of the system, we plot the separation and eccentricity. So now both increase with semi-major axis. So no huge scaling here we have. But when we, discuss further this dependence, but let me point out here that these E and B, the separation here, to which it corresponds to the closing closing super systems, and this is this corresponds to the solar system to us. So 20-ish, right, and also 40 something, they're consistent with observation. So this embodied simulation itself is consistent with the real universe. So then let me introduce new scaling. So hopefully more general than the huge scaling. So far we've seen many times in this conference. So when two gravitational scattering and collisions operating, we expect that equilibrium random velocity is as high as the escape velocity, right? If we equate two time scales, gravitational scattering and collisional damping or collisions. So we have this, so which is known from back, in the 1970s. And now we introduce two-body surface escape velocity for two pairs, colliding pairs, and then also we introduce mean Kepler velocity for this pair. And then, as usually defined, we explain escape eccentricity, or maybe a square root of Safronov number like this. And you like the similar manner to the definition of Hill radius, we now define the length scale. So you see this K is non-dimensional. So now we like to have some spatial scale, length scale with this. So which is K times A. So remember, if you remember the definition of Hill radius, so this is H is non-dimensional Hill radius and times A is the Hill radius. So if you see here, this RK, the length scale, eccentric distance or epicycle amplitude consists of two parts. One is Hill radius here. So which is good because which assures Hill scaling if this is constant. And the other term here is the ratio between Hill radius and the physical radius. So which is responsible for the relative importance of gravity to collisions. They are impact parameters, kind of, for gravitational interaction and the collisions. So now we use this scale, RK, to scale this result. Then they now become separation and extension become almost flat. So for this gravitational collisional dynamics, this RK is more general than Hill radius. Okay, so this RK is kind of extension of the Hill radius to the collisional dynamics. So now for free-floating planets. Okay, so escape eccentricity or root square of Safronov number K is given like this, right? And so far the orbital architecture scaling is only valid, of course, if K is smaller than 1. K is eccentricity. So then what happens? K is larger than 1. Yes, ejection. We expect ejection takes place for this range. So setting K equals 1 gives you the minimum mass of ejected planet or maximum mass of bound planets formed by giant impacts. So which scales with this dependence. So as Yuji already showed you in his talk, if M is small, say like around M dwarf planets, so giant impact formation of super Earths, can lead to ejection. Okay. So now let me summarize my talk. So I investigated the formation of planetary systems by giant impacts through n-body simulations. The results are generally consistent with the observation of causing super Earth systems. And we derived this new scaling, which is a kind of generalization of the Hill scaling. And we expect, so if k is larger than 1, we have ejection, planet ejection. So it's future works. We are now working on the semi-analytical model of giant impact flows, which will be submitted maybe next week. And also we are now expanding this scaling to include the planet ejection. That's all. Thank you.
Yes, thank you. Now you keep open for questions. So I have a question.
Yeah.
So the idea of the radius is maybe kind of local idea, but the ejection means that the eccentricity is close to unity, so it's not a local. So how do you, so the idea is also apply to the ejection as well?
Yes, actually the Yuji's result is consistent with this equation. So yes, I think application of Hill radius, we can apply to a kind of wide system also. Yeah.
Because you mentioned the mutual Hill gradient, so in your simulation, when you place the planets, the multiple planets, what is the mutual Hill gradient?
So we calculate the Hill radius only for adjacent pair. Only adjacent pair. So we calculate, for each pair, we calculate Hill radius.
Yeah.
And then we scale the separation.
Yes, I want to know the value of the Hill radius, mutual Hill radius in your simulation.
Oh, the actual mean number.
Yeah.
Hill radius is, so the non-dimensional Hill radius is say 0.1 to 0.01. Yeah.
So I think there's a criteria to give this size that if this will be in number, then the mutual Hill, the system will go up. Yeah, so I'm wondering, do you see this effect in your simulation?
Yes. Yes, we see it.
Thank you.
Any other question?
Already, so it's often other people have shown that at least for stability, the key metric is either the 1 foot, not the other 1 foot, for planet spacing. So have you looked at scaling things probably with 1 foot?
You mean the instability time scale?
Yeah, so the time scale.
Instability of first collision?
Well, yeah, so usually things collide pretty quickly after crossing, depending on K, I guess.
Yeah.
But these things look pretty flat. It's scaling my whole radio. I wonder if it's even flatter if we did move 1 foot, which probably not a lot of dynamic range to tell. But I'm curious to see experiments that have a really large dynamic range to sort of settle if it's helping like maybe 1 foot spacing. It's really a problem.
Yeah, I agree. The instability time scale is not, scalable with Hill, right? Discussion. But this is about the architecture informed by collisions. So not the instability time scale. So then with this RK, it seems we can scale the architecture, not the time scale. I agree with you. The time scale is not, m to minus 1/3. That's right. But it seems the architecture can be scaled.
Well, even there's usually a critical spacing.
Thank you.
Okay, so thank you.
Thank you.
Kokubo-san.